Yeah, we better. We don't want to miss lunch. Some of us need it. What's that? Oh yeah, yeah, I'm staying in shape. Is everyone back? Seems like there was one missing. Oh, okay. Well, we'll let somebody else teach him how a transistor works, right? Explain to him. All right. Part of this myth now is, again, is this simplicity. So what we're going to do now is turn this transistor on. Before we turn it on, and I left out the switches, by the way, so just imagine there's switches here. We'll get in here and look at the two metallurgical junctions. Now this represents the emitter area. If you recall, that was about the smallest on the transistor. And then here was the base area, which was larger. And just for simplicity, now I've showed the collector region, of the transistor, about the same size, but that's all right. The emitter was N-doped, and we had a P-doped base. And we get a little charge transfer across the metallurgical junction, and then we establish a barrier here, which is the depletion region over the emitter-based junction. And we've got to overcome that barrier with about 7/10 bias to turn it on. And again, that's the depletion region, the emitter-based area, and we'll eventually forward bias that. And now we're going to put the collector bias on. We need that collector bias to collect our carriers. And in so doing, now we had a metallurgical junction originally. It looked very similar to that, reversed, okay? And now we're going to reverse bias it further, and a little more charge transfer, and we end up with a depletion region into the collector because of the 10-volt bias we've applied with our battery. Now, furthermore, now to turn it on, we're going to start pulling electrons out of the base region, creating holes, a higher concentration of holes, and eventually we'll get to a 7-volt bias and turn that junction on and get this flood of electrons across that barrier. We've done that again by applying a forward bias. And in our conventional transistor circuit here, we've got a forward bias. We're conducting current in this direction. We're forward biasing that emitter-based junction. And then, as a result, we've got collector current here, and we get conduction and a current gain because of the way it's set up. Okay. Now, again, we've turned on the transistor with this forward bias potential, created an excess concentration of holes to the point where we have a 7-volt bias now applied across that junction. And we're getting this flood of carriers across the junction. Okay? Now, what happens to them? Well, there's nothing there to move it. Well, we have a flood of carriers, and we have, again, an extremely high concentration of carriers here and no carriers here. Those are the electrons we've just injected across the junction. All right, because of that gross mismatch in carriers, we get a diffusion. Furthermore, the electrons repel each other. So suddenly they start moving across the junction. And when they get across this dotted line here, drew a line on the ground, we have a depletion region. And an electron that gets into this depletion region goes to the positive terminal. And as the flood of electrons gets into the base region, it'll fill some of the holes, if you will, and we'll have to take out another electron to keep that concentration of holes high enough to maintain that 7-volt bias. So we forward bias the emitter-based junction with that 7/10 of a volt, get a flood of carriers, we get diffusion across the base region, and collection in the collector depletion region. And that's how a transistor works. Questions?
How do you turn it off?
We turn off the base drive.
Is that the only way?
I think that's adequate. What, do you have something else in mind? There's, for all practical purposes, that's it. We've got to remove the 7/10 volt bias. And as soon as we turn off the supply, as soon as we quit removing the electrons from the base region, then the electrons coming across fill the excess holes we'd created, and we get back to the original hole concentration with the barrier that was originally there, and the transistor's off. And it's that simple. Well, not quite. I mentioned that the myth is perhaps in the simplicity that I presented here. From this reference that I mentioned, I found this to be the case. Each of these things, and I put a map in here, or a menu. For example, I completely ignored all currents except IE5 and IE4. We get contributions of this base current and emitter current and collector current from such things as recombination in the emitter ohmic contact. That's of some concern, apparently. Some recombination in the emitter bulk. There's recombination in the depletion region, and we use the recombination in the base region, and there's recombination throughout, and we get it up here. There's holes injected, and that's in currents in IB 1 and 2, and no, here's IB 1 and 2 and 3, and IB 4, that's the one we used. Well, you know, it's who could expect to keep track of all that? Well, apparently that's what the physicists have been doing since 1952 when they invented this transistor, or whenever it was. And I showed this to Bill Dawes. You know, I said, look what you guys been doing since 1952. And he looked at it and he says, did we miss any?
Now, can you tell us about saturation and leakage currents?
Oh, yeah.
Okay.
Okay. But for the time being, you know, we got a transistor working, and now we know why, right? Yes, sir.
This is a good question for you. They call the emitter because it emits the electrons. The collector because it collects the electrons.
Mm-hmm.
And it goes base to base.
I guess I really don't care. no, I don't know why it's the base.
Because the
Clue.
number of electrons that flow is based on the
Oh, really?
So they call it base.
Convenient.
Say that again.
Because the number of electrons which are allowed to flow from the emitter to the collector are based on the bias on it.
Some busy bastard thought that.
Would you say that again for the West Coast audience? I believe that, Jack. Okay. Now we'll go across some various parameters and at the same time bring out some other goodies with respect to leakages and voltages and saturation voltages and so forth. Something's crooked. Is that me? Oh, no, I see that. Yeah, it is. Oh, I see. Okay. We don't have a planar surface here. Or the surfaces are unplanar. There's a hump here somewhere. All right. Talking about absolute maximum ratings And again, back to the 2222. Now, it turns out I took this information off a spec sheet for beam lead, and that's how come it's B2T instead of 2N2222. But it is 2222 for all practical purposes. And in that case, we could apply a 60 volt back bias in the collector to the collector base, and we'll see the difference here in a second, as opposed to collector emitter of 30 volt breakdown. The emitter base junction can withhold 5 volts. We can get up to 800 milliamps collector current in that small chip. And we're talking about dissipation here, a half a watt, and that's B3T. I don't remember what that was. Actually, I think in the TO18 package, and I didn't realize that I'd have that problem here. In TO18 package might be 450 milliwatts or something. Close to that, but not exactly the same. In the TO5 package, that larger can with the, well, they all got 3 leads, but the larger small can, it's good for about 800 milliwatts. And if we heat sink it, and that is, again, if we can find an infinite heat sink, something to tie that to thermally, we can get up to 1.8 watts in the TO18 and about 3 watts in the TO5. And it gives us storage temperature range and the soldering temperature limit of 300 degrees C for 10 seconds. And there's a lot of question in my mind why we have to limit that with the processing temperatures we're talking about with respect to that transistor. Perhaps it's just some reasonable practical limit, but the temperatures that you could expose that transistor to are considerably higher than that. Parameters you'll see on a transistor, BVCBO, BVCEO, BVEBO, and then the leakages, some current gains and so forth. And we'll switch pictures here and talk a little bit about that. Now here we're looking at a transistor with a bias on the collector. I just hate to hook up a transistor without some limit to the current flow. They're somewhat unforgiving. It's quite easy really to destroy that thing, and particularly when you're fooling around with the breakdown voltages as you might on a curve tracer just to look at the device. So although maybe my voltages don't exactly match up, we could have say a 100 volt BVCBO and a 40 volt CEO. And now let's talk about some of those parameters. If we're looking at a BVCER, and if that R is a low value, a BVCBO, for all practical purposes, we're talking about the breakdown of the collector base diode. If we look at it on the curve tracer, we have collector current in a vertical direction and the collector voltage shown on the horizontal scale. We'll get a characteristic such as this. The curve tracer will sweep out to about 100 volts and go into breakdown. And on a microamp scale in this case, we'll see a nice clean breakdown. It'll look like one of Hoch's 100 volt Zener diodes. Looks pretty nice. It's a nice clean junction. And then if we open that resistor, because of current gain, in other words, we'll get, as we go into breakdown, we'll get, or as we approach breakdown, actually, as you can see here, we don't actually get to the collector-based breakdown. As we approach breakdown, we'll get some current across the collector-based junction, and it has to come out the emitter. Well, that current through the emitter is what we used a while ago to turn that transistor on. So it'll turn on, and we'll get a current amplification, just as we get a current gain in a transistor. I did fail to point out a while ago, for example, we might have a milliamp in that base drive and 100 milliamps, and that was represented by the wide emitter current shown flowing across the collector base region and the small current that we need to maintain the bias. That current gain, that same current gain, will cause us to get a characteristic such as this. Well, this is highly idealized. You can see a tremendous number of variations. For example, on many PNPs, quite often the BV-CEO characteristic will be almost in line with the BV-CBO. But ideally, and typically on NPNs, we'll see quite a bit of difference between BV-CBO and BV-CEO. And that's because of the current gain introduced when we open the base and get the breakdown current or the leakage current to go through the emitter base junction and result in current gain. Okay, now the term is BV-CBO for the collector base breakdown, and if R is 0, that becomes BV-CES. It's the same, essentially the same characteristic, even though we're looking collector to emitter. And as we increase R to open, we'll get LVCEO, and that LVCEO represents the lowest sustaining voltage. In other words, we can operate the transistor, we'll see that on the characteristics, we can operate that transistor reasonably, I guess we'll say, out to LVCEO. We cannot operate at this point. The transistor characteristic would go up and go into breakdown and probably destroy itself if we tried to operate at, or even, well, let's just say at the LVCEO. That's the lowest sustaining voltage. We get a little negative resistance here as the current increases. We get some increase in gain with increase in current. So we'll see a negative resistance here. And then on up, now we've got the collector resistance affecting the curve above that point. So that's a BV-CER with R equals 0 on the BV-CBO line to R equals infinity at the LVCEO point. Okay, that's the breakdown characteristic. If we looked at BV-EBO, the breakdown across the base emitter, just take the transistor out and turn it around so we get the applied voltage across the base emitter, we'd see essentially the same characteristic, but down around 5 volts. Okay, it's more like a Zener. As a matter of fact, when plastic transistors come out and everything they made was about 12 to 22 cents, they often use the emitter-based diode as a Zener. And it obviously is built just like a Zener to give a 5-volt characteristic. So they would use that. And nevertheless, that's the BV-EBO, and we'd see this characteristic at 5 volts instead of 100. Okay, other parameters there, the HFE. I'll show you some characteristics on HFE. I do have notes here somewhere. No, I don't either. All right. Using this. Again, the HFE, if we now put a battery bias here, and to turn this on as we did in our operating the transistor mode there, we get, say, a milliamp in here and 100 mils out here in the collector and emitter. Actually, we've got 1 mil base drive, 100 mils collector, and 101 mils in the emitter. Okay, we don't store that. We conserve our charge, and Kirchhoff's law still holds and all that stuff. Okay, the spec might indicate at 100 microamps collector current, we'd have a gain of about, what does it say, 75 typical. At 1 mil collector current, we have a gain of about 125, and at 10 mils, 175, and 150 mils, a gain of 200. And then at, whoops, I didn't get the last one, did I? 500 mils, it falls off to 120. And I'll show you a typical curve on a device in just a second. Let's go on with other parameters on the spec sheet. We got a VBE on. That's the base drive voltage to get a particular collector current. The same thing applies in the saturation region. Now, saturation voltage. If we have 100 mils collector current and require 1 mil base drive to sustain that current, again the 101 mils here, the 1 mil is all that's required. Now we may have 100 mils and 12, 14 volts. That's a lot of power, but nevertheless we could have, depending upon the relationship of this resistor to the collector and base drive currents, to go into saturation. Then if we raise this base drive, we would tend to raise the collector current. But perhaps this resistor is large enough so that if we had 10 volts and 100 ohms, all we could get is 100 mils. If we can get no more than 100 mils, we can go up in base drive 1, 2, 3, 5, 10 mils, and all we're going to get is 100 mils. That's circuit limited. But the voltage from collector to emitter will fall as we increase the base drive. We're overdriving the base, and that collector voltage will fall down perhaps to 1/10 of a volt. What does it say at saturation voltage? 2/10 of a volt at 150 mils. And now it's essentially a resistive situation, and it may in fact be 1/10 of a volt at 100 mils. All right, we'll talk about 150 mils since it says 2/10 of a volt. Now, the reason for that is not perfectly clear. We might come up with some myth if we worked a little while, come up with some myth as to why a transistor goes into saturation. What people like to say, the physicists like to say, is that because we overdrive that base emitter, we actually forward bias the collector base diode. And in that condition, in the saturation condition, we'll have a VCE sat, which is equal to V sub F of the base emitter diode minus V sub F of the collector base diode. Collector base diode being much larger. So it'll have a lower forward voltage, and the end result is we'll have, say, 7/10 volt minus 0.55 volts V sub F of the collector base diode, and we got our, no, it was 0.2, wasn't it? Okay, let's go 0.9 VBE on and 0.7 V sub F of the collector base diode, and the difference being 2/10 of a volt, and that's the saturation voltage. So that's the transistor in the on condition and saturation. Does it leave you with any questions? All right, and then again the VBE sat, the base drive voltage and saturation, will be considerably higher because we're overdriving. Instead of driving with 1 mil for 10 mils collector current, we'll drive it with 10 mils for 100 mils collector current. We'll get that 2/10 volt difference in saturation voltage, and the only price we pay is a slightly higher VBE sat. Okay.
Now,
Yes, sir.
why do they expect the small signal gain at 100
Oh,
megahertz?
okay. That's a good point. The 100 megahertz is, Dennis probably won't let me call that RF, but we're trying to find some limit in frequency of what this transistor will operate. And so we'll put in the condition being 20 volts on the collector, okay, and 20 milliamps collector current. Well, it'll be set up such that we operate precisely at the right base current to get us those conditions. And we'll couple in a small AC signal and look at the, say, the current gain across this load resistor, and that ratio then becomes the small signal current gain. The voltage drop across that resistor, of course, indicating the collector current. And that ratio of the base current to the collector current will give us a small signal current gain. And because of the high frequency and losses in inner base capacitances and parasitics in the package and so forth, we'll have a much lower current gain. We'll hit about 4 as a maximum. That's a gain of 4 at 100 megahertz, and that says that we can get AC gain up to 400 megahertz. At 400 megahertz, the gain will be 1. So we lose the chance of any power gain or what have you. And above that, the gain is less than 1. The transistor is useless from 400 megahertz on up. See? But below that, we can get an AC current gain below 400 megahertz, we can get an AC current gain with this transistor. So we get into a power transistor, and it might be 150 kilohertz. You know, nearly 3 orders of magnitude less in AC current gain. Okay. And if you notice the next parameter on that list there is the transition frequency, and it mentions 400 megahertz, and that's from current gain to no current gain at 400 megahertz. And then some indication of the size of the junctions. They give a collector base capacitance of 8 puffs max, and the emitter base capacitance, because of a much closer set of plates across the depletion region of the base emitter, we get a much higher capacitance. So we've got 25 puffs as a maximum on the emitter base input capacitance, as opposed to the collector base capacitance of 8 puffs. Okay. Now let's move right along here. Gets what I want. Graphics plot. This is the collector characteristics I was talking about. We could pick out this point, which I'd marked. That turns out to be 80 milliamps, and that's 500 microamps, or a half a mil base drive at 80 mils collector for a gain of 160. Okay? That particular device. I did that in our 4145A parameter analyzer in the lab. Or actually John Saylor's office. Now what did I show here? Oh, what I've done now is, let me go back to this. I want to blow up this area right here. This is our saturation area on the characteristics. So we'll blow that up just by expanding the voltage scale. And you have to ignore this flag up here. That's because of the machine. Got a 100 milliamp limit on the machine. So if I got a 100 milliamp limit on the machine and I'm driving it with 10 milliamps, then that line cuts off at 90 milliamps. See? So now let's just ignore that part of it. Go back down here. We've got 30 millivolts per division. And if we use a force beta of 10, we can only get to about 90 milliamps. But we're showing 150, about 160 millivolts collector saturation at 90 milliamps. Okay. I should have finished describing the graph first. That's a 100 milliamp at this point. It's 10 mils per division, and that's collector current. And this is the collector voltage, and it's actually collector emitter voltage. It doesn't specifically state that. So we, to get it into saturation, we overdrive it. And again, at this point, we were looking at force beta 10 with, well, roughly 10 milliamps base drive at 90 milliamps collector current. That's the collector saturation characteristic. And we did this to show the base drive voltage, and that was in saturation. I believe that's right. We're in saturation. So essentially the same set of characteristics we showed on saturation voltage. Oh yeah, that was the other plot. We're showing the base drive voltage. So we hit it with 2 milliamps, and essentially with no collector current at this point, we have a, what's the scale? Oh, 15. We've got 0.75 volts. If you remember on the graph, we were talking about 7/10 of a volt to turn the transistor on. And then as we increase the collector voltage, we get an increase in collector current. We get to close to 100 milliamps with that 2 milliamps base drive. And that's what that shows us VBE sat in this case. The VBE on, of course, would be just a little bit less because we're not overdriving. We got a little more than 10 times the current we needed in the base drive for saturation. Okay, so that's that particular characteristic. We talked about HFE as a function of current. I didn't have a handy dandy plot for the 2222, but this is a 2484. Instead of being an 800 milliamp device, it's only 50. On the current scale, a log plot, that was 10 milliamps. This is 50. And the current, or the HFE is 100 here, therefore it's 10 here, and 1,000 here. We're getting 300, a gain of 400, and that's at about 3 mils, and it falls off to a gain of about, whoops, where am I? That's 200 at 50 milliamps, okay? And what I wanted to show here was the temperature effects. This is another one we might need a myth for. I got a list of things that I did have that are temperature dependent. Anybody see it? I don't know what I did with it. Oh, temperature effects. Temperature effects within the transistor affect the carrier concentrations, the mobility. That's how easily do the carriers move, referring to electrons and holes. Diffusion coefficients, how easily the carriers diffuse, say across the base region primarily here. Excess carrier lifetime, how long do the carriers live in the base region. Emitter efficiency. What's the difference between the electron and hole current across the emitter junction, and several others. The end result is, if we cool that transistor from room temperature to minus 55, we can get a current gain change from 400 to about 160. And that's a rather significant increase. So when one is designing a circuit, and you're going to have to operate at low temperature, you certainly have to take into account the gain variation with decrease in temperature. Now, if we go from 25 to 125, the other end of the military temperature scale, we essentially are come close to doubling the gain. So the gain is 400 here. It'll be close to 800 at 125 degrees C. Well, I certainly didn't think that this would last this long. I'm just now beginning to think about op amps. And while I'm looking for my notes here, somebody got a question on the transistor section here.
Yeah.
Mm-hmm.
All the devices that you've been talking about have been bipolar. Do you only find MOS transistors on ICs? That is.
No, they're discrete MOS and JFETs, and that's where does that start? We have that scheduled, some considerable discussion on MOSFETs and JFETs, and next week, I think, Tuesday, yeah. So we'll get into MOS transistor. Good reason I'm not in there discussing that too. Okay. Operational amplifiers. Got to throw a few circuits at you. Operational amplifier is a gadget right now, and one of the principal parts of an operational amplifier is a differential amplifier. Now, I couldn't find this particular drawing for a bipolar, completely bipolar. We happen to have JFETs on the input. If you just picture that now as an NPN transistor, and here also, and let's talk about collector and emitter, and well, they want to call that a gate, but that's all right, we'll just call it RG. Anyway, the differential amplifier can be analyzed readily if you just look at it as a simple emitter-follower amplifier. And that's going from from scratch to a lot of circuitry in a hurry. But what this amounts to is we can look at this emitter follower amplifier representing the differential input amplifier of the operational amplifier, and we get a gain expression something like minus RC over RE plus RG over beta, and what we're getting at is that things are arranged properly. This one stage of the amplifier can give us a gain of 10 to 100. Okay, so we'll have that kind of a gain, and then we put this into the total operational amplifier circuitry. We can see our input as a differential amplifier. There are the two input terminals, and we go across another stage, a differential amplifier, and then we get into a third stage, which is really called a level shifter. And what that amounts to is, on the operational amplifier, we can have these two terminals, which are really close, always close together in voltage, essentially zero differential. It's the incremental difference in these two input terminals in voltage that provides the signal for the operational amplifier to adjust itself on the output. So these two are allowed to shift from V plus to V minus for all practical purposes, and as long as they're together, it's called common mode. As long as they're together, the operational amplifier will still function virtually over that entire range, plus power supply to minus power supply. So we have then here a level shifter such that regardless of the input, we can drive this output from essentially 0 volts, plus or minus. Okay? Hello? That's our operational amplifier, somewhat simplified, quite a bit simplified as a matter of fact, but it does show that. And to get the total gain, open loop gain, we can look at the gain of the individual stages, and typically we're talking about a gain of 10 to the 5th to 10 to the 6th. That's 100,000 to a million. That's not uncommon in the open loop gain of the operational amplifier. Now what do we do with that thing? Well, Hoke said I had to put up these silly symbols, so we're going to put them up. And I'm sure most of you have seen this representation of the operational amplifier. And what do we do with this thing? Well, generally it's used in analog computation. And we have here an inverting amplifier, and what that amounts to is, input terminals. This is called a non-inverting terminal and an inverting terminal. In other words, you put a signal in on the inverting terminal, we get a positive signal in and a negative signal out. If we put it in on the non-inverting, we put a signal in on the plus, we get a positive signal in, we get a positive signal out. You notice a somewhat difference in the input circuitry. Otherwise, we're putting a signal in here on this voltage divider, we're grounding the voltage divider here and putting the signal on the floating terminal. But if we have, say, a 1 millivolt signal in, it tends to move this terminal 1 millivolt above ground, okay? And we move it above ground on the input, it comes out below ground on the output, and it'll be a gain of 1,000, 50K to 50 ohms. We get about a volt out, and what we've done then is get a volt across 50K and a millivolt across 50 ohms, and we have essentially the same current. The ideal amplifier says we don't want any currents. See? We're not going to use any current. So that's the way this thing responds. We tend to increase this, upset that differential amplifier, which would, give it more base drive. We don't want that to happen, so the amplification says we need a volt out here and we take that input base drive off the front end on that terminal. So that's essentially the operational amplifier. Now, we talk about analog computation. We can get down here to the summing amplifier. We put in 3 signals here. This is a summing point, and the output of this amplifier, to reduce that current to 0 in the input, will be a voltage proportional to the sum of the signals on those 3 inputs. Okay? So that's the scheme. If we wanted to make another analog computation, we could replace this. Let's get back up here. We could place this resistor with a capacitor, and we have a differentiator. We'll get a signal, because the capacitor takes some amount of time to charge, we'll get a signal proportional on the output to the derivative of the input signal. And we put a resistor back in here and put a resistor here, and we'll integrate that input signal. See? So we're doing various analog computations simply by changing the input impedance from resistive to capacitive, and then the circuitry as well. So that's the idea of the operational amplifier. And since you know how transistors work already, that's about all you need. I do have a sample which I just added this morning, post haste, that shows the absolute maximum ratings. Parameters, really what I'm after. Absolute maximum ratings, of course, we can talk about, I guess it's me, huh? Focus didn't change, did it? Not a very good graph, view graph. Differential input voltage plus or minus 15 volts. Now it does say voltage between V plus and V minus terminals can be as much as 40 volts. Okay. Differential input voltage is limited to plus or minus 15 volts. That's the inverting and non-inverting inputs maximum signal allowed, 15 volts. Operating temperature range, storage temperature, peak output current 50 milliamps. That's a function of the size of the output transistors in that 4th stage in the amplifier we saw a minute ago. Power dissipation 300 milliwatts, and that should be no, that is unquestionably somewhat limited, probably device limited. Normally you can take peak current. Oh, I didn't have that. Yeah, peak output current times the plus and minus 15 volts on the power supplies and come up with maximum power dissipation. That'd be 30 mils times 50 milliamps is 1,500, but it won't do it. Obviously limited to 300 milliamps. Offset voltage. I guess I really should go back to that operational amplifier. And we'll all keep this in mind. Talk about the rest of these parameters. Offset voltage. Now if we take off this signal and let this set at ground, we've got 0 differential on the input, okay? They're both shorted to ground. But because of imperfections, you know, the physicists just don't have this quite figured out yet, or the processing people, but really, it's the physics of the situation that gets us in trouble. Instead of having 0 volts on the output, we're going to have some voltage, you know, plus or minus on the output, non-zero. Now, to return that voltage to 0, we don't want a signal out if we don't have one in. We have to offset the input. Now, you can actually bias the input, either terminal, such that you do get exactly 0 out. Most operational amplifiers are fixed with an additional terminal I haven't shown, we haven't talked about, where you can actually adjust with a voltage divider, a signal, a small signal, not on the input precisely, but on the input differential amplifier, to adjust this output to 0 volts. So the offset voltage is a measure of the, without the offset adjustment, of the difference, or of the output voltage with a 0 input signal. That's offset voltage. Bias current. Going back to the original circuit, if we have an input bipolar transistor, we've got to have some input bias current. Ideal amplifier says infinite input impedance, but practically we will have an input bias current. And that is, that could be significant depending on the output impedance of the signal source driving the amplifier. The another parameter being, well, both transistors on the inputs will have a bias current. The difference is the offset current, input offset current. They both have a bias. The difference is being the input offset current. That's also specified. Common mode range, and that's again the range of voltage that you can move these two signal sources when tied together, somewhere between the plus and minus power supply, called the rails. And there is a limit because of the breakdown voltages of the input transistors. And transfer characteristics. When you look at large signal voltage gain, essentially if we open this and put a microvolt in here, are we going to get a volt out? See, that's open loop gain. Put a microvolt signal in, a volt out, gives us a 10 to the 6th open loop gain. Output voltage swing. If we put in a maximum signal on the input, this voltage should go all the way to V plus. But we have to have some load on the output. Consequently, we'll have some saturation voltage drop on that output transistor in the amplifier, and we won't quite make, say, 15 volts. Maybe it's 13.75. That's as high as we can go. And the same thing applies to the negative power supply. Saturation voltage on the bottom of that output stage. Transient response. In spite of the wonders of the world in the transistor area, it takes time to get a signal from here to the output. So we'll be given a rise time. How long does it take that signal to move up the slope? We'll be given a slew rate. No, that's the slew rate. The rise time is related to that in time, just a different way of looking at the rise time of the transient response of that amplifier. Settling time. If we look at this really in detail, we'll see a bit of a delay time and a slope on the rise, and it may overshoot. It'll take time for that to settle down to that precise 1 volt. And that's a measure. And in cases here we're talking about nanoseconds, so it's pretty fast but not perfect. Power supply current. In this particular case, the 2520, we're talking about 6 milliamps max, typically 4 milliamps. That's the bias current to keep our operational amplifiers in the active region internally. Power supply rejection ratio. Oh, I didn't talk about common mode rejection ratio either. If we move this, the input terminals tied together from the positive power supply to the negative power supply, we should get no change in the output because there's still 0. But in fact, we will. Again, because of the imperfections in the amplifier. So the change in voltage on the output compared to the change in voltage on the input, again with both terminals moving up and down, common mode, we'll get a power supply rejection ratio, and that's given in dB, and they're talking about, I don't see an input, or common mode rejection ratio of about 90 dB. And the same thing applies if we hold these two terminals at ground and change the power supply voltage, say from plus or minus 15 to plus 5 minus 15, or vice versa, or move them both down to plus or minus 5 volts, we should get no signal out, but we do get some, but that voltage ratio indicated is up to 90 dB in that case too. Any questions? I'm ready to quit. I'm all through.
Okay, we'll see you.
But we will, what's,